We're recording. It's been a while.
Hello.
Hello. And we are in two new places.
Yeah. Where are you, Mr. Kirk?
I am in room 346.
Wow.
Third floor, back of the building, by my little ivory tower.
I'm in portable 3.
Portable 3.
Where the plebes are.
The
but at least you
plebes.
get fresh air.
But I've been trying to get Mr. Ostrander to hook me up, and I can be in a portable with you and Miss Coleman.
Yeah, it's pretty fun.
We should get Miss Coleman to be a guest star on one of these one day.
Sounds good.
Yeah. All right. People don't know who Miss Coleman is, but that needs to change. All right. So let me go ahead and share my screen because I was about to just proceed without sharing my screen like I do probably every day. And we are recording, right?
We are. Can you drop the commie link?
I can drop the commie link. Boom. Upload to Google Drive. Authorize Google Drive.
Wow.
Hopefully I'm not giving away.
So
there's my password. My password's ...
Wow. I wonder if the students are skipping past this or not.
I hope.
Or we should tell some jokes so they don't skip past it. What is 10 to the negative 12th? Degaios.
Wait, what? What is 10 to the negative 12? Degaios?
Mm-hmm.
10 to the negative. Is pico the term for like that many zeros?
Yeah, 10 to the negative 12 is pico.
Okay.
So it's pico.
Is that bigger or smaller than a nano?
It's smaller because the exponent is negative 12 instead of negative 9, I think.
Is nano's negative 9?
I think. Don't quote me on that, though.
Right, what's my joke? I'm going to steal my joke. It's from STEM Arts Night. But why are freshmen scared of, why do freshmen walk on the sidewalk? That's what it is. I ruined the answer.
Because they're scared of Street. You shouldn't be scared of Mr. Street, though. He's like really nice.
He is, and he makes delicious coffee. All right, let's go ahead and get started. Hopefully you guys fast forwarded through that. Are you in?
I am.
Cool. All right, so we are doing a topic that some of you may have seen before because it is in the geometry curriculum. But with everything going on, maybe your class touched this, maybe they didn't. Doesn't matter. We're going to dig deeper than a geometry class does anyways. Welcome to the Law of Sines Pre-Calc edition. So I have the Law of Sines here. So this is kind of lame. We have the formula. We're going to try to prove it. But hopefully I prove it here in a way that you've never seen before. This is a really cool proof. I'm actually going to do one thing before we get started, Mr. Contreras, and I'm going to rewrite the Law of Sines in a completely different way. Not completely different, a slightly different way. I'm going to reciprocate each one of these equations in this extended equality.
Wow.
A over sine A, B over sine B, and C over sine C. Just another version of the Law of Sines, and there's a reason why I like the one on the right way more. And hopefully I can justify that claim on this page. All right, so we're going to prove the Law of Sines. A over sine A is equal to B over sine B equal to C over sine C, or sine A over A, sine B over B, sine C over C. I have a circle here, Mrs. Contreras.
Mm-hmm.
And we want to prove the Law of Sines, which has A's, B's, and C's, and also sine A's, sine B's, and sine C's. So we need to develop some sort of relationship between sine A, sine B, and sine C, the angles, and the lengths A, B, and C. Can I actually say that real quick? Capital is an angle. Lowercase is a length. You can kind of see that over here in our picture. All right.
What's that D doing?
What is that D doing? It's just hanging out.
Okay.
Why do you think that D is there?
Well, it looks like it's placed very carefully so that going from D to B is a diameter.
Let me go ahead and draw that diameter. I like that a lot.
Oh, and that's nice that it's D then, because it's like diameter.
Let's go ahead. This is going to be kind of annoying, but I think we can balance the letters. I'm going to go ahead and call this length lowercase d.
Okay.
Normally, lowercase a and angle A are across from each other in a triangle. And in this triangle that we've been given, A, B, C, A and A are across from each other, B and B are across from each other, and C and C are across from each other. With our new triangle, D and side D are not across from each other. So let's just keep that straight. Okay, we have this diameter.
I also see that C, it looks like it's horizontal, and it looks like the line from A to D is vertical. So that maybe makes me think that that could be a right triangle. I don't know if I can justify that.
Can you give me letter names to describe this right angle you speak of? Because can we agree that angle A is vague right now since there's a lot of angles happening at A?
Maybe it could be angle A plus something else.
Well, so do you remember from geometry how we name angles?
Sure.
If you don't, that's okay. We angle symbol, and then we give 3 letters.
Oh, true. Okay.
The middle letter being the vertex, I guess we could say, of our angle.
So then angle dab.
Nice.
That's what I want. Yeah.
You're claiming that angle dab is the measure of angle dab is 90 degrees.
We're doing degrees again, right?
Wait. Let's see. Yeah, we're doing degrees again. I used to have a little thing on this page that said you are now permitted to say degrees. So let's just say blanket statement. We are allowed to say degrees now.
All right.
So angle dab, 90 degrees. I'm going to quickly say why it's 90 degrees. Because you claim that you're hoping it's 90 degrees. It totally is. There's a theorem in geometry called Thales Theorem. I could actually be pronouncing it wrong. It's Greek. It might be Thales. I'm not sure. There's some debate on how to pronounce the name. Thales Theorem states that no matter where you draw the vertex of the angle, if a point on a circle extends to a diameter, it will be 90 degrees. No matter where you extend an angle, if it intersects a diameter, it will be 90 degrees. Actually, a fun fact, the angle of C is going to be half the angle measure of the arc made at AB. And the angle that on a circle, when it intercepts the circle, its angle measure is half of the arc span that it intersects. Am I making sense?
Yeah, it totally makes sense. Yeah. Which also extends very nicely to Phaley's theorem, where you have if you have it going all the way across, then that angle is pi. And so then what you have half of that is pi over 2 or 90 degrees.
I love the fluent changing between radians and degrees. That's great.
It's called code switching.
Yeah. Awesome. So we have length D, and its angle that's across from it is a 90-degree angle. You are correct in saying that it is. Why is that useful to us in this scenario?
Because we love using right triangles with our sines and
sines
cosines,
and cosines
for that matter.
We need a right triangle to do sines and cosines. So let's see. Can you give me a we need a sine. We need a sine angle. What's the sine of I'm not 100% sure where I want to go with this yet, but we need to introduce a sine somehow.
Okay.
Okay.
Well, angle C isn't related to our right triangle like at all.
Yeah.
So should we not
what's the sine of D? What's the sine of D?
Sine of D is like BD, angle BDA.
Yeah. BDA. What's the sine of angle BDA? dA.
That's length C over length D.
Length C over length D. And I'm going to go ahead and get rid of my BDA. Can we agree that angle D, there's only one angle there?
Yeah.
Angle C, there's only one. There's a bunch happening at B and A, so let's be really specific with those. But for now, D and C, we can kind of call them one letter.
Okay.
And sine D is a C over D. Okay. Remember that theorem? I didn't give it a name, but that intercepted arc theorem?
Mm-hmm.
What's the relationship between angle C and angle D?
Oh, those are going to be the same.
All right. They're intercepting
because
this.
It's arc that it has from arc AB is the same.
Arc AB, the intercepted arc for angle D and angle C are the same. Exactly. All right. So sine D is equal to C over D. So what can we say instead?
Sine C equals C over D?
Yeah. We're actually really close to the law of sines. Right? Sine C is equal to C over D, right? Because C and D, let me write that right here. Angle C is congruent to angle D.
Yeah, we're like roughly 1 inch from the law of sines, actually.
Mm-hmm.
It's like right there.
Right. So yeah, so can you move this around so that we get to one of the three equalities?
So let's see. What can we say about like changing D into something else?
Well, no, before that, just like this equation right here.
Mm-hmm.
Can you move it around for me so that we have sine C over C or sine or C over sine C?
Because we can just take D and swap it with sine of C. So sine C over, or sine of C over sine of C.
All right, here's the big realization.
Okay.
What is C over sine C equal to?
Well, according to the law of sines, it's supposed to be equal to all those other things.
Okay.
But it's also equal to the diameter of our circle.
C over sine C is equal to the diameter of our circle. Does that set any sparks off in your brain to how to proceed?
Well, we just need to get A over sine of A to show that that's like the same as the diameter.
We chose C and D and B and A arbitrarily. We could draw our right triangle completely differently so that we are going from C through the diameter to the other side of the circle, or from A to the other side of the circle. Do you want to do it one more time, or do you want to make the claim that A over sine A is also equal to the diameter?
I think that that's fair, right? That we can do this without loss of generalization.
Yeah, right. We chose angle B, or coordinate B. We went through the origin to the other side, drew a right triangle to point A. We have a right triangle here. We did this process and we found out the diameter is equal to C over sine C. Doing the same thing with the other two coordinates. C over sine C, A over sine A, and B over sine B are all equal to the diameter. I made this claim at the beginning that I like the right-handed, not the right-handed, but the formula on the right-hand side. We have two different law of sines here, one reciprocated of the other. I like this one on the right-hand side because it's also equal to the diameter of the circumscribed circle made by our triangle. Another quick geometry theorem. If you give me any triangle, there is a unique circle that goes through the 3 points. So by circumscribing our triangle, we now have a circle of which that circle's diameter is equal to the law of sines. This other one is equal to the reciprocal of the diameter. So it's not that much worse, but I really like this other one because it's also equal to the diameter. Yeah.
Yeah. I also like that because it makes you think that like each of the side lengths, like that A, B, and C, those are all scaled versions. They're scaled down from what your diameter is. depending on what your sine of that angle is.
It's either going to be equal to or smaller than your diameter, because the diameter is the furthest distance between 2 points on a circle. Interesting. So that's how you have a side A. How do you scale it to the diameter? You multiply by 1 over sine A.
Or cosecant of A.
Yeah. Oh, yeah. Ooh, I like that. I like this perspective. I've never thought about how sine A or sine B and sine C, cosecant A, cosecant B, and cosecant C are just scalar multipliers to take a side length to a diameter. That was a mouthful, but really interesting to me. There's a law of sines, right? We're going to use the law of sines a bunch, but I think my favorite part about the law of sines is its elegant reasoning. Let's do an example. I got one for us here.
All right.
All right. Example, solve ABC. So do you know what it means by to solve a triangle?
Find all the things that you don't know.
Yeah, find all the things that you don't know. How many things are in a triangle?
There's 6 things because there's 3 angles and then 3 sides.
Yep. So we want to find A, B, and C. And we want to find angle A, angle B, and angle C.
You're about to write angle.
I usually write this little chart too, just so I know I got everything. And I like to fill it in with everything, even the things I already know. This is totally optional. It's just what I do.
All the lights turned off because I haven't moved enough. I'm going to go save the lights back on.
I'll add while you do that. We got the side opposite B is B. So B is 10 centimeters. The side opposite C, we don't know. The side opposite A, we know nothing about A or angle A. And we know angle B, 51 degrees, and angle C, 40 degrees.
Hang on. So we do know what angle A is.
We do?
Because don't all the interior angles of a triangle, they add up to 180. So if we have 91 is like the rest of it, then it's got to be 89 degrees.
Ooh, that is very close to a right triangle. Can you code switch from 51 to radians?
51 times pi over 180. It's the Google Translate version.
What's 180 times 51 divided by 3.1 for one? Okay. 89. So you summed 51, 40, and then angle A. And actually, to be real technical, some people might be screaming at me because their teachers in middle school really cared about this. But usually I measure angle A. I personally don't care at all. And then you did a little bit of math and you got 89.
Yep.
Sweet. Cool. So I'm gonna go ahead and add that. 89 degrees. Measure angle A. And I'm just gonna go ahead and write it. 89. So the 8's awful. Yeah, it's an upside down heart. It's not much better. Okay. All right. So far we have not used the law of sines at all.
Okay. I guess you want to use the law of sines then, huh?
I think so, yeah.
All right, that's fair. So
unless you know the law of cosines by heart.
So we got, well, that's in the next page. We haven't discovered that yet. So we can set like B over sine of B equal to other things. Because B over sine of B is 10 over sine of 51. And also whenever you're using a calculator, make sure that you are also telling your calculator to read your mind by switching it into degree mode if you've been in radians this whole time. And so then you should get a number. And then from that number, you can figure out what your other things are.
And cosecant times, no, we're not gonna get into that, but I really like this idea that secant of 51 is the scale factor that takes 10 to the diameter. I've done this for so many times. I do it in the summer when I do geometry, and I do it. Wow, I like that. Anyways, so
joy of co-teaching.
Yeah. So we got 10 over sine 51 is equal to, I like to do my best to use the degree symbol. And that's going to be equal to, we don't know A or C, that's what we're looking for. Let's do A first.
And sine of 89.
Sweet.
So like what I would do just to like work efficiently is save that number for the diameter like just store it in my calculator if I'm using a calculator, and then just multiply that by sine of 89, recall it, and then multiply that by sine of, what was it, 49?
Yeah, so we could write A is equal to the diameter times sine 89, and C is equal to the diameter times sine of C, which is 40. I really like this new way of thinking. That's really cool. What did you get for the diameter?
Math.
Oh, I thought I got the
Let me
vibe
pull it
that
up.
you were plugging into a calculator. Maybe you were.
No, I was just talking about how much I like math. Do I have a calculator in here? I might.
Oh my gosh. Oh, I have a calculator. Should I break mine out? Boom.
Wow.
This is
Do you have one of those
blue.
fancy colorful ones?
Blue.
You're so cool, Mr. Kirk. Look, I have the good
Blue.
old-fashioned public school
Oh, nice. That's a TI 82.
TI 83 plus. Excuse you.
Oh, it's a plus? Okay.
Yeah.
I thought it was one with like the anyways. Mine's dead.
All right. Well, that's what you get for being fancy.
I got a charger on my bag.
So you got 10 over sine of 89. I checked that I'm in my mode. So this is
Sine of 51, I think, right?
oh, 51. Okay, that makes more sense.
The wonders of doing math together.
Yeah. So we got 12.86759.
8675309. That's funny.
No.
12.8675, so 866.
Sure.
I like to go to 3 decimal places. I always say because that is what the AP Calculus exam asks you to do, and
That's true.
yeah, just so everyone knows. 12. That is the diameter of the circle. I'm not going to be able to draw it. Oh, no, not bad.
Actually, maybe you should try to use the circle tool. See if that
It's kind of
works.
hard though, because you have to find something called the circumcenter.
Okay.
I believe that is where the angle bisectors intersect. That's going to be like your center of your circle. Let's see if I can get it. Nah. Can I like move the circle once I've made it big enough?
I think so.
Nah.
So you switch to the,
Oh,
you can move it.
let's see if it works.
There you go.
I'm like really close. I'm like really
Yeah,
close.
it's pretty good.
But the circumcenter is down here, so maybe I think it might be where the side bisectors, the segment bisectors intersect.
Mhm.
There's a bunch of different types of centers of triangles: incenter, circumcenter. There's another one, orthocenter. That's for another day. Maybe you learned that in geometry, everyone. All right, what is the diameter times sine 89? Let's get A.
12.866.
Wait, isn't that the diameter? Oh, wait, but sine
it's
of
like-
89
Mhm.
is
It's
very
like
close to
very
1.
close to 1.
Wait, so this was 8665. Wait, no, this was 8765, right?
It was, so the diameter is 12.8675.
867. Oh, so it should be 868. I'm sorry, I'm getting these numbers wrong. Everyone at home's like, that's not the right number.
Rounding.
866. So it is a little bit smaller. We made
It's a
the
little bit
claim
smaller.
earlier that these numbers will be smaller than the diameter. The diameter is the maximum. And that only occurs when you have a right triangle.
And we have an almost right triangle. So we have almost the diameter, but not quite. Okay. And then for the other one, it's 8.271. And then I rounded that for you, so we're not confused.
So 866, 8.271.
I'm also not sure, do students know how to store things in their calculator? I feel like that was something that like everyone always assumed that I knew, but I didn't always know. If you
Let me
hit
get
the
this.
store button,
866.
the store, oh no, it's like focusing on my face.
Let me stop the
So
share real
it's
quick
just-
so we can see it a little bit better.
So if you hit the store button, yeah, right there. And then like do a variable, which I like X because it's just one button. So then you can get like X times sine of stuff. That's very not clear. There it is. Kind of. Right. Good enough.
We could definitely showcase this in class as well.
You can also include screen shares as comments in Comedy, which is pretty cool.
Ooh. Is that new?
I don't know. I just learned about it last week.
That has to be new. That has to be new. We would have known about that.
I don't know. I feel like we feel that a lot. We're just like,
Yeah,
oh, I
sure.
should have known about that.
Well, speaking of which, I have just learned so much more geometry just from this problem. I've done this problem before, but doing it with you, I've learned so much.
Ooh.
This 12.8. I also like realized if you draw the circumcircle around a right triangle, the hypotenuse will be the diameter. I don't know. I'm like wowing myself right now with geometry facts. This is exciting.
So cool.
All right. We have some more geometry to get to. So let's knock it out. The law of cosines. My proof of the law of cosines is not as elegant as the law of sines. No circumcircles, no beautiful. The law of sines is actually equal to something. The law of cosines, actually, it kind of is the Pythagorean theorem. Do you see that?
Yeah, because you're like kind of moving stuff around, right? Like you're taking this and then you're like taking away something.
Mm-hmm.
And so, yeah, that's Pythagorean-y.
Yeah. So it's basically a Pythagorean theorem with like a little error that we're adjusting for. Negative 2ab
yeah.
cosine c. I don't know.
That's a nice way of thinking about it.
Yeah.
That like this, we're taking away the error of, yeah.
The not
nice.
rightness. Right, because when, oh my gosh, because when it's not a right triangle, the hypotenuse is the diameter.
Mm-hmm.
When it's not a right triangle, the hypotenuse is smaller, or the longest length is smaller than the hypotenuse. I don't know. I'm just like,
so it's getting taken away. Yeah, that makes sense.
Oh my gosh, the law of, okay. So hopefully everyone has seen the law of cosines before. If you haven't, that's okay. Once again, it's in the geometry curriculum. It's prereq for this class, but we're living in a crazy world. So if you haven't seen it before, we're going to get a proof here. And then we'll use it a couple times. We're going to use it this one twice. All right. Proof of the law of cosines. I've been saying constantly Pythagorean theorem, Pythagorean theorem. That's my hint to you here, Mrs. Contreras.
Okay. So can we say that c squared equals h squared plus a minus x squared?
C squared is equal to h squared plus a minus x squared. Is this what you said?
Mm-hmm.
Cool. Right, because what we've done is we've dropped an altitude. And that's going to give us a right angle. Right? Given this is an altitude, it's the right angle.
Can we also make another equation using h squared plus x squared equals b squared? Is that allowed?
Yeah. I mean, these are both facts. Given any triangle, if you drop an altitude, these new lengths that we've created will satisfy the Pythagorean theorem.
Okay.
We have these two facts. Okay.
So now it feels like we need to kind of combine these two equations that we've made, probably solving for h squared and then substituting it in so that we don't have to deal with h squared anymore, because that's kind of something that we made up. And then.
So I've just written h squared is equal to b squared minus x squared.
Okay.
That's just based on the idea that you said solve for h squared.
Okay. Now, can we take that h squared and substitute it in for what we have in the first equation? So we can get c squared equals b squared minus x squared plus the quantity a minus x squared. Oh, and I guess we could also expand out what we have with a minus x quantity squared. So that's what a squared minus 2ax plus x squared. Is that right?
Mm-hmm.
Okay. And then chop, chop.
Chop, chop. Whoop-pow, whoop-pow. All right, so I'm really impressed because I've never seen someone, you told me beforehand that you've never taught a geometry class, and this is your first time teaching pre-calc. So you've never had the chance to teach the law of cosines or the law of sines before.
Mm-hmm.
And you're like, you have done a flawless job so far, effortlessly. I'm like, I'm in a really good mood right now. Before we started this video, I was exhausted, I was tired. I proctored the SAT all morning.
Mm-hmm.
Man, I got like a second wind.
Nice.
All right, c squared is equal to b squared plus a squared minus 2ax. That's like pretty much the law of cosines.
Right, because we just need to kind of like massage this a little bit, because the only thing we're missing is this x, which we don't have in our, can we peek at the law of cosines again just to see where we're going? Yeah. We want that x to be b cosine c. So how can we relate b and cosine c? This is kind of like a we're kind of sandwiching in on the proof,
Yeah.
but that's okay. It's valid.
Yeah. So we have been given the law of cosines. So it's not as organic as maybe it once was 2,000 years ago when the Greek philosophers were knocking this out.
But like, whatever, it's fine.
But whatever. We know where we're going, so we're gonna get there.
Yeah.
That's
Can
the
we look at
beauty
the
of living in
picture
the
again?
future. Yeah.
Yeah, the future. This is the future. Okay,
So
so
I'm gonna bring this up. X equals B cosine C. Is that true?
where we have x is b times cosine of c.
What's the cosine of C?
Cosine of c is x over b.
X over B, right?
Mhm,
That's just like adjacent over hypotenuse in this right triangle.
mhm. And then just smush the b over. and
Move the
there
B
you
over.
go. That's what
X
it
is B cosine C. This is, in fact, a true statement. Proof. QED. Mini little proof on the side. Love it. All right, so X is B cosine C, so we're done.
We are.
All right, usually I'm kind of bored when we do the law of cosines because it's like very algebra-y and there's no like beautiful diameter law thing, but I enjoyed that nonetheless. That was awesome.
Ooh. Math.
And I love this new way of thinking about it. It's the Pythagorean Theorem. And if it was a right triangle,
That cosine c would be 0.
0. But if it's not a right triangle, that diameter, the longest side of your triangle is going to get a little bit smaller because the diameter is the max.
So then
I don't know if people are understanding what I'm saying, but
But the closer you get to a right triangle, while you're using the law of cosines, the smaller that little error is going to be. Right?
By the way,
So
are
then
you
that's really
enjoying
nice.
the fire trucks outside?
Yeah, I hear them too. It's like we're at the same location.
It's like, yeah, it's like we're like 150 feet apart. I wonder if I can see you if I look out the window.
I doubt it. Because there's a portable in front of my portable. There's no way.
Okay. Beautiful.
Nice.
Let's proceed. Let me go ahead and scroll down.
Okay.
We have the law of
Boom!
you have oh my gosh. That is a good crap.
And this is like minutes ago that I did this.
Oh my god.
This was pre-law.
Is this
of
when you were
cosines.
talking when you liked math, when you were talking about math?
This is when I wasn't using the calculator. Yeah, that's exactly right.
So I want to take a moment before we proceed to these problems and talk about the different types of patterns you can be given with a triangle. So in geometry, we learned that potentially 3 of the 6 measurements define a triangle. Given 3 sides, side, 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 that defines a triangle. If you give me 3 sides and you put them together, there is only one triangle, a unique triangle. Similar with side, angle, side. That's the example that we've been given here. If you give me a side, an angle, and a side, there's no 2 triangles you can draw. There's a one unique triangle. There are, I think, there's a lot of patterns. Let's figure out what they all are. So we have side, side, side. We have side, angle, side. Side, angle, side is specifically when the angle given is between the 2 sides given. Right? If I give you a side, I give you an angle, and I give you a side. That defines a unique triangle. What other patterns are there?
Well, we had one before that was 2 angles.
That was
for the law
angle,
of cosine, law of sines. It was
angle, side.
Angle, side.
Right here, we were given. Let me stop moving around too much. We were given an angle. We were given an angle, and we were specifically given a side not between the 2 angles. So we say angle, side. And that defines a unique triangle.
Mm-hmm.
What else?
Does angle, side, angle, does that work?
Angle, side, angle does define a unique triangle. If I give you an angle, I'm going to give you like a dotted line. If I give you an angle, a side, and another angle, regardless of these lengths, they will intersect at a unique point, and you will have defined a unique triangle.
Because
an
they're
angle,
lines.
yeah. We say inclusive or exclusive when we're talking about these sides and angles, by the way. inclusive angle, exclusive angle. We got some more patterns, and you've actually given me many of the ones that do define a unique triangle, but some don't.
Like angle, angle, angle?
So angle, angle, angle. I'm actually going to do a little line. Angle, angle, angle. Or I'm just going to say, because you made this point earlier in this problem, given angle, 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 you didn't really need one of those angles. We were given 51, we were given 40, 89 wasn't given, but it's implied. So we actually just say angle, angle. But angle, angle does not define a unique triangle, because if I give you 3 angles, if I give you 2 angles, there is an infinite number of triangles you can make. You can make a triangle that big. You can make a triangle twice as big with the same angles. If I give you 2 angles, we can dilate that triangle without changing the angles. All right, there are 2 more here that, well, actually there's 1 more here that we're missing, which kind of, there's 2 more things I'm gonna write, but there's only 1 more situation.
Side, side angle?
Side, side angle is the last one. And we're gonna talk way more about side, side angle in the next video. Very specific side, side angle triangles. But if I give you a side, an angle, and so we have this angle here, we have this side here. If I give you another side specifically across from the angle that I've given you, there's potentially 2 triangles you could make. A little swingy action. You can take that side. If I give you angle, let's say this is like 40 degrees and this is like 10. If I give you a side that's 12, we could have the side come down here or the side come down here. Actually, that's a bad example. That triangle doesn't exist. If I give you like a 9, there's multiple triangles you can make. So side, side angle, we don't get a unique triangle. Angle, 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 we don't get unique. The last one we call HL, hypotenuse leg, which is a special case of side, side angle. If I give you a hypotenuse and a leg and a right angle, there is a unique triangle.
Because you know the hypotenuse is part of a right triangle and it's across from the right angle.
Yeah. So those are our scenarios. And when we are given angle, angle, side, the law of sines is the move. Right? When we're given side, angle, side, the law of cosines is the move. What I would like to do is attempt to draw this triangle before we begin.
Okay.
What I like to do is I like to take my longest side, which here is 11, and I just draw that kind of flush with the bottom of the page.
Mm-hmm.
Then I like to draw my angle C on the left. It's about 20. Thanks for adding those little notes on the side.
Yep. It was ambiguous to me because it looked like League of Legends.
League of Legends. I mean, that too. And then I like to draw my side B, which is 5. So B equals 5. A is equal to 11, which is a little bit more than double 5. And this is about 20. My pro tip is give yourself the best sketch you can give. Right? And what we want to do is we want to find this side.
And also the other 2 angles.
And also the other 2 angles, yeah. But now we've given ourselves a triangle. And that's my process for side, angle, side. Give your longest side. The angle is inclusive, so then do the angle. And then do the smaller side. And base that side on the kind of how long is it compared to the other side.
Looks good.
All right, so can you use the law of sines right now?
No, because we don't have something that gives us the diameter. We don't have like the number across from another angle.
Yeah, I like to say we don't have a pair.
Pair.
Yeah. So when given side, angle, side, we must use the law of cosines.
All right, we can do
angle,
that.
angle, side, we have a pair, that this angle and this side. Okay.
So we have C squared.
Which is we don't know. Yeah.
And that equals what? A squared plus B squared minus 2AB cosine C.
2A which we know 11, B cosine, and we do know angle C 20 degrees. Right. One thing we didn't say before is the law of cosines also works for A squared equals B squared C squared minus 2BC cosine A. It's all arbitrary. What you call letter, and it also works for B squared equals C squared plus A squared minus 2C CA cosine B. Just the important thing is this letter and this letter are opposite each other.
Mhm.
Okay, back down here.
Cool. So I plugged that in and I got C squared is 42.634.
634.
And then square rooting that, we get 6.529.
6.529. Cool.
That makes sense.
Yeah.
This is a really small angle. And then B plus C is like pretty close to 11.
Real quick, I do want to add a fun fact about triangles. 20. How do I want to say this? All right. What's the relationship between A and C and B? Like compare them.
A is bigger than C and B.
A is bigger than C and B. That's exactly where I'm going with this. What do you notice about sides A, B, and C?
A is longer than B and C.
Can you conclude from this small observation a fact about triangles?
That the angle and the pair is like match up.
In terms of like magnitude?
Yeah. Or order, I guess.
Yeah. The largest angle is opposite the largest side. The smallest angle is opposite the smallest side. And the medium is opposite the medium. I guess we can call it.
So fun.
Fun times.
All the motion sensor lights.
Yeah. Okay, so we got 6.529. That is going to be opposite the medium angle. And B is opposite. It looks like B is going to be smaller than 20 because 5 is smaller than 6.529. So an interesting fact about triangles that may be useful later. Cool. Okay, how do you want to get these angles?
Law of sines.
Let's do it. I like law of sines because there's way less going on there.
Yeah. So
I'm going to change colors.
C over sine of angle C.
So the diameter, not 20, sine 20.
And I'm getting 19.091.
For B or for the diameter?
Diameter.
Okay.
So that's what I'm saving. And then I'm going to multiply that by what?
Sine.
Oh no.
Oh no.
Because we don't
have the angle. We can't use this technique.
All right. Bummer.
Well,
we can reciprocate it.
We can still know that 19.0. But anyways, which one do you want to find? A or B?
A.
A, because once we find one of them, we can find the
then
other.
We can subtract.
Yeah. Let's do A because something's about to happen actually. So A, so sine A down here, and 11 on top. Let's do a little bit of switchy. We got sine A is equal to 11 divided by 6.529 and sine 20 in the numerator. Are you calculating?
Yeah, I'm getting lost though. So we have 11 sine
20. You see what I'm doing though, right?
Yeah.
Cool.
So we get 0.576.
0.576. And then what do you get for A when you take the arc sine?
35.186.
All right. How do you feel about that answer?
It seems small.
It seems small, right? Don't you feel like if C is 20 and I claim that B is smaller than 20,
that means that whatever we have left needs to be like 140 something.
What's the range of the arc sine function? in degrees.
Arc sine goes from sine 0 to sine 0, right? So then that's pi. So 90.
So the arc sine will output angles up to 90 and as low as negative 90.
Sorry, 180. Wait, no, I'm confused again.
So this is the arc sine function.
Mhm.
Let me see if I can get it. Pi over 2, negative pi over 2, which you said earlier was 90 degrees and negative 90 degrees.
Mhm.
When you plug a number into the arc sine function, it will never give you an obtuse angle.
Boo.
This was a big problem back in geometry for many people. Is when it output the angle 35, you had to know that answer's wrong. Let me supplement it. Let me find its supplement.
So that's
Right.
180 minus that.
So if you use the arc sine, if you look for the largest angle first, you're gonna get the wrong answer.
Mm.
Unless all of your angles are acute, which is possible. If one of your angles is obtuse and you go to try to get it with the law of sines, you won't get the right answer. I'm very glad that we went for A first so we could talk about this. But what should we have done?
Go for B.
Yeah, go for B. Always go for the smallest angle first. And you know which one's the smallest because we have all the sides.
True.
Yeah, so let's replace that 11 with a 5.
Okay.
Let's replace this A with a B. And I'm just gonna replace this 11 with a 5 and this A with a B. We're gonna get some number. It's gonna tell us what B is.
0.262.
0.262, and then it's gonna give us an acute number.
15.184.
That's right, because it's totally less than 20.
Totally.
And then now we don't need to use the law of sines or arc sine on the obtuse angle. A is just 180 minus 20 minus 15.184.
Which is 144.816.
Which happens to be the supplement of the other angle that we got, that 30 whatever.
Yeah.
35.1 something.
Mm-hmm.
And so if you get the wrong angle, you can supplement it.
Yeah.
But my pro tip here is always go for the smallest angle first.
Nice.
All right, so I'm not going to go to the trouble here to organize my answers, but we got C, we got angle B, and we got angle A.
Sweet.
And then we were given 3 sides, so we have all 6. All right, I love this example. So side, side, side. We cannot use the law of sines because we do not have a pair, given no angles, no pairs. What do you think we should do?
Well, if we can't use law of sines, then we should use the law of cosines,
Mm-hmm.
and then solve for one of the angles. And then from there, we can use the law of sines.
Let's do 25 squared is equal to 10 squared plus 12 squared minus 2 times 10 times 12 cosine C is the angle I'm using.
All right.
A little bit of like weird stuff happening here. Okay, so 25 squared, that's 625. I'm going to do this until you tell me an answer. 20 times 12, that's 240. 625, 525, 425, 425. That gets us to 385, 385, 381.
381 divided by 240 is 1.5875.
But we got a negative 240 by the way.
Mm-hmm. Okay. So
Okay,
you have the
but-
negative 1.5 stuff, but then that's not possible. You can't have cosine of something is giving you something where the magnitude is greater than 1.
Look at our side length.
25 is greater than 10 plus 12, which is 22. So it's not a triangle,
Yeah,
Mr. Kirk.
So I said earlier, side, side, side defines a triangle. Not if those 3 sides don't dimensionally work. 25, if you have the side length of, what is it? 10 and
10
12,
and 12.
they'll never reach.
Oh, so sad.
So sad. So sad. This is not a triangle. All right. The triangle inequality is at play here. 10 plus 12 is not greater than 25 in order to be a triangle. The two sides must always sum to larger than a third side.
Wow.
No matter what combination you take. All right.
This
So
looks
that
like a
was my,
crab.
yeah, this is kind of like a crab. I was thinking the same thing. I do have a real side example.
All right.
I even called it the real example.
The real example.
So I'm really glad I got you. If you watch this video back later, you can see the way I phrased my question, hoping you catch it faster. But it was good that we did it, because that's what's going to happen. You're going to get a domain error.
Oh man, that would be a really mean quiz question, or a really nice one.
Or really nice. In fact,
Like
I've
no
given it as a
calculator,
quiz
do this
before.
problem.
All right, so side, real example. I'm going to go ahead and try to draw my triangle. It's not going to be great, but it's going to give me a good idea of like what might be obtuse, what might be acute. 9's my longest side. I'm going to draw that flush with the bottom. 7, 5. This gives me a decent idea which angle is the biggest. This is C, so that means this is angle C. This is B, so that's angle B, and this is A. So quick quiz. What's the largest angle?
A.
Okay. Justify it.
Because 9 is bigger than 7. And
It's not bigger than 5. Okay. And then what are you feeling?
Go for C, because it's the smallest. No danger there.
No danger. If you went for A, you'd be a fool. Once we get C, well, actually, no, rewind. With the law of cosines, the range of the cosine function, the arc cosine function, is 0 to 180. The law of cosines will always, in a triangle, give you the correct answer. It will never give you the supplement. So just so everyone's clear, we could go for A right now if we choose to use the law of cosines. The law of sines is where there's a problem. Arc cosine of theta. Arc sine of theta. Arc sine is where the problem is. I hope that's clear to everyone. But let's still go for the smallest angle, because that's common practice. That's a good thing to get in the habit of. Want to make it clear though that you could use the law of cosines on A right now if you wanted to. All right, so 5 squared cosine C. 7 squared, 9 squared minus. Fun fact, I would say 20% of people every year forget that too. So this is, heed my warning. The most common mistake I see when using the law of cosines is simple copy error, or a simple forget of that too. All right, or you want to calculate it?
I got 33.557.
33 for C.
For C.
Nice. So 33.557. Do you want to use the law of cosines or the law of sines to get our other angle?
Probably the law of sines, just because it's slightly less effort.
Yeah, but now it matters. B or A?
We should go for B.
B, because it's acute. Is it possible to have two obtuse angles in a triangle?
No, because your interior angles need to add up to 180. So if you have two obtuse angles, then you're already over 180. So you don't have any more angle to give.
You have negative angle to give. I wonder if there's like some sort of geometry out there that allows it. Probably
good, right?
Though.
Like geometry
yeah, like
on like a sphere. Yeah.
But yeah, we should go
Like
for B.
Both of us were immediately like, yeah, there has to be.
I was gonna say something. It was along the lines of what we're talking about. Yeah, never two obtuse angles. That way you know your two smaller angles will always be acute. So B must be acute. All right. B, which is 7 over sine B, is equal to sine of 33.557. Do you have that saved in the calculator?
I saved it now.
Sweet. And I'm going to put a 5 on top. You like to save it in your calculator, respect it. I like to just leave everything in calculator ready form for the very end. So I might have even like gone to the trouble to like call RC arc cosine of whatever that number would have been. And then plug that in here. I don't know.
Yeah.
Sine B is 7/5 sine 3.557. B is equal to.
Sorry, I'm being slow.
It's okay.
Sine
Don't apologize for speed.
Yeah. Okay. So 0.774. Oh, then sine.
Is that sine B?
That is sine of B.
So B is equal to 0.774. That means the y coordinates 0.774. It's going to be bigger than 45.
It's 50.704.
50.704. I know I think 0.71 is the sine of 45. I don't know. It doesn't matter. B is 50.
What are we missing?
A. The potentially obtuse. A might be acute. You can have 3 acute angles. We know that A is, and in fact, it's going to be obtuse.
It's going to be.
Yeah.
Yeah.
50.704. And then what did you get for the angle A?
95.740.
Let me write this real quick.
74. Yeah.
557. And then you're getting what?
95.740.
740. And we would have gotten the wrong answer if we had done the law of sines for A. We would have gotten 85. And you might have not noticed that it was wrong. It was much easier to notice it was wrong in the previous problem. 95.704. 740. Right, that angle, it's a little bit bigger than 90. Yeah, be careful when you're using the law of sines. But we know what is causing the problem. That's the key, is to know what's causing the problem. Like this isn't, computer science where you're trying to find a comma somewhere in 50 pages of code. I don't miss those days. All right, this video is getting a little bit long, so we're going to close it out here. Sorry, everyone, for making this one lengthy. It's going to be a chill weekend, though, because we're not giving any major assignments on Wednesday and Thursday this week.
So nice.
Yeah.
I'm giving a project that's due next Friday.
I mean, that's as good. I mean, hopefully it's a good project and it's exciting and fun.
They're making games. It's gonna be cool.
I want to see what kind of games they make so I can like start to craft this project for everyone in this class.
Sweet.
All right. It's been a while since you've been here, Mrs. Contreras. Any words of wisdom?
Wash your hands
and wear a mask.
Yep.
Oh man, I'm excited to see
Although I
people
can't
that are
put
coming
the
back.
mask
Be careful out there, everyone. And yeah, I don't have any words of wisdom. I'm not wise. Let me stop my share. And it's been a while. I'll let you close this one out.
Oh, nice. That was a really bad one.